Guess I'll begin. Okay. Good afternoon, everyone. I'm Charlie, and I will be presenting Beyond Black-Scholes a Bayesian reinforcement learning approach for option pricing today. So I'll begin this presentation by just introducing a little bit of the context, so we can all have a general idea of the terminology here. So the first one, what is an option? So an option is basically a financial instrument that gives its holder the right but not the obligation to buy or sell an underlying asset at a predetermined price. And the option pricing is basically just to use some ways and forms to determine the price of the options. What are the methods to accurately price the options? So I'll basically get into this section in the next slides. And there are two different types of the methods already established. One is for supervised learning method, and the other one is the parametric models. I will go deeper in the next slides. And identification of the research gap. There are not many researchers using RL approaching the option pricing problems, especially combined with neural networks. And that's where our work began. And this research will improve the trader's trading experience by providing a more accurate prediction on the option prices. So that's enough for the context. So previously, there are some parametric models have been used for pricing options. There are Black-Scholes, the famous Black-Scholes equation, which basically use the geometric bounding motion as a stock path simulator. There has the Merton jump diffusion models, which incorporates the jump points in the financial markets. There's also Houston volatility models, which is also a model that incorporates the jump points in the financial markets. Those are very good approximations, but the real world stock prices are not actually generated by these underlying processes. So after that, some people has using a non-parametric model, such as a supervised learning model, to eliminate the biases identified before, and therefore it's better to produce a better predictions than the parametric counterparts. However, as we all see that training a supervised learning model really requires a large amount of the data, which is pretty difficult to acquire in our today's websites lives. So what if we don't have enough data then? Which brings us to the reinforcement learning. Reinforcement learning seems a really good way to solve the problem. Our predecessors on this project, they proposed using a policy-based neural network that learns only from the historic price of the underlying asset instead of the actual option price. In this way, they overcome the limitation of the supervised learning models by not just limited to historical option price data that I just said, and it also overcome the limitation of the parametric models by not relying on a specified stochastic processes. And they also design a reward function, also called a loss function in the neural network, using a delta hedging principle where the risk is mitigated. I will get into the delta hedging principle the slides after. So they also implemented the results from a paper and it extended to geometric bounding motion with jump diffusion process, which is equivalent to the Merton jump diffusion processes, because their goal is to incorporate the change point to use reinforcement learning algorithms to detect the change point in the financial market. So that's why they incorporate the jump diffusion processes in the network architecture. So their previous methodology here, the delta, wait a second. The delta hedging principle here, the main idea of it is just to hold some kind of share of the stock to offset the risk incurred from the changes in the value of the options. So as you can see in the equations, the relationship between the change of the underlying asset prices, which is the change of the S value, and the change of the option prices, which is the change of the C values, they are in a linear relationship. So this is what proposed by master students in Norway's University of Science and Technology in 2017. But his work is not successful because he only assumes that the relationship of the the underlying asset prices and the option prices are linearly, but actually in reality it's not. So what we did is we start by further expanding the loss function using Taylor expansion and the delta hedging principle incorporated together. We modify the boundary conditions for the neural architectures, and I will basically explain the very big Taylor expansion here. So let's take the first look. Take the first term here, the delta C over delta S. We call this one a delta, like it's a Greek term. We call this a Greek. A Greek means a Greek here in our research represents the like the differential of some first order or second order or third order rate of changes. So by incorporating more Greeks, our main objective is to add more Greeks in the loss function so that theoretically the loss function should perform better, and the prediction of the RLAN framework of the option prices should be fit perfectly with the Black-Scholes and the Merton-Jump diffusion model. That's our theoretical things, but it actually turns out that it doesn't work in that way at all. So as you can see here, the estimated gamma values for given underlying asset prices is just an example of one of the Greek terms that we added. And you see the reinforcement learning ANN has overfitting problems, like it cannot fit the Black-Scholes solutions, which is supposed to be the exact solution. And but we also propose that it could be probably because we only use the random seed generator in TensorFlow instead of actually buying the real options. Because if we buy the real data, like the ANN could probably fit a little bit better than the Black-Scholes, but it's only an assumption. So no, actually, we haven't been there yet. So here is another graph about the estimated option prices given underlying asset price. As you can see that the ANN cannot fit the Black-Scholes perfectly, which is supposed to be the exact solution. So that's where our work began. The research hypothesis, very long, I will just read that. We first start by fully exploring the loss function and the combination of different hyperparameters of the ANN-RIL framework under both the geometric Brownian motion and the Merton-Jump diffusion conditions. If the problem is solved by maximizing the architecture of the artificial neural network, then no further actions are needed to be taken. If not, we proposed a Bayesian neural network that should solve the dissatisfaction of the ANN-RIL framework by generating a confidence interval in the prediction process of the option prices. So our work begins by hyperparameters tuning. The hyperparameters tuning process tries to find the optimal hyperparameters combinations of the proposed artificial neural network reinforcement learning framework. And we experience a large amount of the constraints, and we run tons of the experiments. It turns out it's actually a huge combinatorial optimization problem because it's so many hyperparameters, like so many combinations, and it's still running on the server. We are using GPU to run it, so hopefully we can gather enough data. Right now, the current best combination, although it's running already for a month, under the geometric Brownian motion condition, the best hyperparameter is 5e. For a learner rate is 5e to -4. Number of hidden layers 120. Number of training epochs 2100. Number of batches is this. Number of batch sizes is 21,500 with 11 years of training. So as you can see the results, before is like that. After tuning, we got that. The curve is almost fitted. So that's for Black-Scholes and ANN comparison because it's using GBM. And now we also have another one under MJD condition tuning. Before tuning, we have this. After tuning, we have this. So as you can see, the curve is almost fitted together with also the Merton-Jump diffusion process, which means that previously the curve is not fitting together. It's not probably caused by the higher order Greeks, but also probably caused by the architecture of the neural network. We also added a lot of more Greeks like charm, eta, kappa, mu into the loss function. Each represents a different partial differentials in the previous section that I just stated in the very long Taylor expansion. And we also modified the boundary conditions and we got the following results. So I will just show the sample results for the charm because they are pretty similar to each other. And I guess we don't have that much of time. So with charm, as you can see that there is still a big discrepancies between the prediction by the ANN and the Black-Scholes. After this is after tuning, the curve is still not fitting together, still overfitting. So and the Black-Scholes is supposed to be the exact solution. So there's still a very big problem existing in the neural network. So which brings us to further explore other aspects and satisfaction of artificial neural network. The first one would be why do we want to maximize the likelihood? Evidently, like it's lack of theoretical justification, and also why just point estimates instead of predicting a range of the predictions on the option prices. From a practical point of view, this type of training usually results in overfitting problems, like just in our cases. Therefore, we proposed a Bayesian neural network for option pricing. The Bayesian neural network, the main idea between this, behind this Bayesian neural network is the Bayes rule. Here is a sample of the Bayes rule. The probability of event A given event B is true is equal to the probability of event B given A is true times the probability of independent of A divided by the independent probability of B. We all learned this in high school, so I'm pretty sure everyone knows that. And I'll just put the very simple words here. The methodology we use is based by backprop, and it's just an algorithm that we used. I found a paper, I found a code, but I found it's hard to follow. So in the end, the supervisor supervised me. We changed to another one. Like it's pretty similar idea behind this, LSTM or something like that, but he's basically using this to implement the Bayesian neural network. And the main idea is to take ANN out and adjust BNN and its corresponding loss function and the neural network architectures. Sample result. Here is just a sample results. These results, as you can see, there are 4 lines here. I'll explain. So theoretically, we will get a boundary value of the predicted option prices. Predicted option prices. There's an upper bound and there's a lower bound. What we want is the actual bound, like the actual option prices, to fit in between the cube, so that the problem is solved. And also there's a prediction curve here, which is just our ANN, like the ANN point estimates, the result of the ANN point estimates. So that's for the BNN, but we are still waiting for the hyperparameter tuning code and the further loss function expansion in the ANN. If that thing can be solved, the BNN is just for comparison purposes. Like we also take the initiative to compare the quantum with the finance, because both are the probabilistic fields, and there's a very interesting parallel between these two. In quantum mechanics, the position of a quantum particle is a random variable. In finance, the security price is also a random variable, both random. We also have 2 PDEs, partial differential equations. The Black-Scholes on the left, a very famous PDE. The Schrödinger's equation on the right is also a very famous PDE. They're also PDEs, and the H equals this one. So if we, go back a little bit. Okay, so if we express the Black-Scholes equation into the Schrödinger form, we will get the quantum Black-Scholes equation, which is like this. And if we take a step even further, like rearrange the graphs and take the Hamilton, I don't know how to pronounce that, Hamilton constant of the HBS here, and we will finally find out that the solution for the Schrödinger's the quantum Black-Scholes equation is actually the same as the Black-Scholes equation. So our next step would be compare the RL, the reinforcement learning efficiency, and the accuracy on the learned solution for both the Schrödinger's equation, the quantum Black-Scholes and the actual Black-Scholes. So conclusion. Option pricing is really a difficult field of study. What can work today may not work tomorrow. Although the application of the work is quite narrow, only to price options, evidently, the work is still part of a novel reinforcement learning paradigm in which the neural network is used to approximate the partial differential equations. And we also believe that our work will not only be have potential values to those who wishing to test the options, but also to the reinforcement learning community as a whole. And that's the end of my presentation. Thanks for listening. I will begin to take questions.
Okay, so thank you, Charlie, for your presentation. Now I would like to address the judges and ask if you have any questions. We can only take one question due to time constraints, but if you have other questions, you can send them in the chat. Thank you.
Jason here, I can ask. So just a sort of clarification that,
right.
So that, right. You know, each of the so-called Greeks, like you mentioned, charm there. Each of the right. Greeks is really sort of an nth degree partial derivative. Is that correct?
Yes.
And then,
yes.
And then by sort of including more of these, you have basically more variables to train upon. Is that the correct interpretation?
Yeah. We plan to add more Greeks in our function.
Great. And options people just use this terminology, the Greeks, and that each one means a certain degree partial derivative of a function.
We call that a Greek because it looks like a Greek.
Yeah.
Call it others.
Sure.
Okay, thank you, Charlie, again for presenting.